Hello everyone. So we already have started discussion related to thermal sensors. We have seen that we can take an electrical equivalent of a thermal sensor or thermal sensing situation to understand how thermal resistance may influence the temperature sensing overall. We have taken a situation where you have an object and then there is a temperature sensor attached to it. So this is your sensor, and then we have drawn a simple schematic related to the sensor and the object. This is the object temperature, then we have taken the sensor temperature, we have taken the environmental temperature. This is the resistance between sensor and object, this is the resistance between sensor and the environment, because this sensor is also connected to environment, so we have taken that also into consideration. And then we also have seen that there is a capacitor which is related to the heat storage part associated with this schematic or associated with this thermal sensing. We also have seen that in certain condition we will never reach, or the sensor temperature will never reach the object temperature. So your TB will be always different from TS if the del T is not equal to 0. Del T is nothing but the difference between the object temperature and environment temperature. So if this difference is not equal to 0, then we can never reach the object temperature, that is the sensor temperature will never reach the object temperature. Then we also have started discussion regarding the dynamic condition associated with the thermal sensing. So for a dynamic condition, what we have seen is, if the surrounding temperature changes with time, or the sensor temperature is not yet stabilized after coming in contact with the object, in that case the incremental amount of transferred heat, that is dq, will be proportional to delta T. Delta T is again the thermal gradient. So to make it more simple, what we can do is we can take an example. For example, if you have a object A and you have a object B, and if the temperature gradient, that is the difference between temperature, that is TA and TB, if we take the temperature associated with object A and object B, if the difference is quite high, that is the delta T is quite high, then the incremental amount of transferred heat will also be higher. We can say that from the normal heat transfer considerations, right? So in that case, the dq can be given by alpha 1 TB minus Ts into dt. Similarly, the absorbed heat, for example, if the heat is getting transferred from A to B, then B will absorb the heat. Then this absorbed heat dq can be given by m into C into dt, where m is the mass of the object, C is specific heat associated with the object. Or we may consider this as dq dash, because your dq and dq dash may not be equal. However, in the next slide anyways we have said, if there is no heat loss, that means no heat is getting lost anywhere. So it's only the thermal transaction between A and B, two objects, in this case the object and sensor. Then your alpha 1 Tb minus Ts dt will be equal to m into c into dt. This is the equation that we'll get. And then from here, if you do some rearrangement of the equation, you will find dTs divided by Tb minus Ts is equal to alpha 1 dt divided by m into c, right? And then we also have seen we can consider this as time constant, that is tau t, which is nothing but it's given here m into c divided by alpha 1, actually this should be 1 by tau t. So, your tau t is actually m into c divided by alpha 1, which is nothing but m into c into R1. R1 is the thermal resistance. In case of electrical circuit, electrical RC circuit, you will find time constant is nothing but RC if it is an RC circuit. R1 here, the electrical resistance is equivalent to the thermal resistance over here, and m and c is nothing but the quantification of the thermal energy that is getting stored, which is equivalent to the capacitor. So, your time constant in this case is m into c divided by alpha 1. Then we replace this value in this equation, we will get dTs divided by Tb minus Ts is equal to dt by tau t. Now, once you solve this equation, you will get this equation, right. Now, let us see the derivation of this particular solution. So, in this case, let us start with this equation. So, what we have done in this case is we have considered Ts is equal to x, Tb is equal to A, and then so it's equal to A. So, let me write it properly. So, your Ts is equal to x, Tb is equal to A, and then you have considered tau t is equal to B. Now, if you take this equation, which we have already seen over here, then the equation can be rewritten as dx divided by a minus x is equal to 1 by b integration dt plus c. C is integration constant. Now, let us consider a minus x is equal to y. So, in that case your equation will become, so if a minus is equal to y, then minus dx is equal to dy, replace dx with minus dy and a minus x with y, then your equation is minus dy by y is equal to integration of dt is t. So, t by b plus c, integration of dy by y is nothing but log y. So, it is minus log y is equal to t by b plus c. Put the value of y over here. So, it is minus log a minus x is equal to t by b plus c. So, your a minus x is nothing but e to the power minus t by b plus c. So, actually there should be a bracket, but it does not matter because c is anyways the integration constant. You can consider it as minus t by b plus c as well. So, it's, I mean, that won't make a difference because c is anyways integration constant. So, your x in this case is a minus e to the power minus t by b plus c. Put the value of x, which is Ts. So, your Ts is equal to, put the value of a, which is Tb, Tb minus e to the power minus t by tau, because value of b is tau t. So, t by tau t plus c, or you can write Ts is equal to Tb minus e to the power c into e to the power minus t by tau. So, this is an equation and this is the constant value. So, as I have said, even if it is minus c, it will come as e to the power minus c, but it is a constant anyways. So, it does not make a difference, right. Now, this is what the equation is. Now, at t equal to 0, consider Ts is equal to T0. that is the initial temperature. Here T0 is the initial temperature. So your T0 is equal to Tb minus e to the power c. Just put these values over here. If your T is equal to 0, then this becomes 1. So your Ts is T0, so this will be T0. So your T0 is equal to Tb minus e to the power c. So the value of e to the power c is Tb minus T0, which is del T. So ultimately you get this equation. Replace the value of e to the power c with this initial condition. So your Ts is equal to Tb minus del T into e to the power minus T by tau. Now if you plot this equation, it will look like simple RC circuit equation, right? So at one time constant, that is when your tau T is equal to tau T, and if you calculate this value, you will find that the temperature will reach 63% of the maximum value, that is Tb. So from this plot, it is very clear that the temperature will reach to Tb at T equal to infinity, right? Even in the equation also it's like if T equal to infinity, then e to the power minus infinity is 0, then your Ts is equal to Tb. Otherwise your Ts, the value of sensor temperature, will never reach Tb. And then the other situation is if your delta T is equal to 0. However, in practice you will find that delta T is not equal to 0, because there will be certain sort of difference between the object and environment. In most of the cases, you will find that delta T is not equal to 0. So from this consideration, it is very clear that your Ts will never reach Tb. It will reach Tb at T equal to infinity, or if your delta T is equal to 0, right? Now, if you consider your T is equal to say 5 tau, 5 time constant or 10 time constant, probably your sensor temperature will be very close to your object temperature, which is good enough. So one thing is very clear from this plot is that if your tau is very small, then your sensor response will be very high. So it will reach close to Tb with less amount of time. So smaller the tau, faster will be the response, right? Then so far we have considered your R2 is equal to infinite. Where we have considered that? Because we have considered there is no heat loss. Then only we will get dq equal to dq dash, right? But if your R2 is not equal to infinite, in that case there will be another term which is alpha 2 Ts minus T0, that will also be included in your equation, in your dq equation, right? And then your absorbed heat is m into c into dt, and when you equate both the equation now, you will find alpha 1 Tb minus Ts dt plus alpha 2 Tb minus T0 dt is equal to m into c into dTs. Previously this term was not there because your alpha 2 was very high, right? So we did not consider this term because there was no heat loss. So there was no heat transfer between the environment and the sensor. But now we have this term because you have an R2 present. And then if you do some rearrangement in this equation, you will find alpha 1 Tb minus alpha 1 Ts plus alpha 2 Tb minus alpha 2 T0 into dt is equal to m into c into dTs. Again rearrange this equation, take alpha 1, this Tb term together, you take Tb in common, so it's like Tb into alpha 1 plus alpha 2, and then here you will find minus alpha 1 Ts minus alpha 2 T0, you take minus in common, so it's alpha 1 Tb, it should be Ts, I think, yeah, so it should be Ts plus alpha 2 T0 is equal to m into c into dTs. Okay. Then again I mean, in this case, you can understand that this equation will become alpha 1 plus alpha 2 Tb, alpha 2 T0, alpha 1 Ts dt is equal to m into c into Ts. Just rearrange this equation, but you have got it over here. And then if you take or divide the entire equation with alpha 1 plus alpha 2, you will find that Tb minus alpha 2 divided by alpha 1 plus alpha 2 into T0 minus alpha 1 divided by alpha 1 plus alpha 2 into Ts dt is equal to m into c divided by alpha 1 plus alpha 2 into dTs. So, it should be suffix Ts, right. So, your equation will look something like that. And we know that your alpha 2 is anyways much higher than alpha 1. Then you can consider it's like alpha 2 divided by alpha 2, because alpha 1 is very small. So, it will be like Tb minus T0. So, Tb minus T0 is nothing but your del T dash. In this case, we have taken it as del T dash. And then your equation will become Ts is equal to Tb minus del T dash minus delta T e to the power minus T by tau T into K. K is again the proportionality constant, integration constant. The moment you do the integration, you will find there is a constant which is K in this case, right. So, after this arrangement, so in this case, please consider this as Ts, right, it is not Tb. So, here it is like alpha 1 plus alpha 2 Tb here, then minus alpha 1 T0, that is minus alpha 1 Ts. We already have mentioned this over here, okay. So, that is the equation. When you solve it, it will lead to this particular equation. And if you plot this equation again, now you will find that you have a Tb minus delta T dash always present. That is, if you consider your R2, then your Ts can never reach to T0. Previously, we considered there is no term associated with that R2 because there was no heat loss, but in practice there will be some sort of heat loss. In that case, there will be always a difference. Previously, it is like Ts is equal to Tb minus delta T e to the power minus T by tau T, right. But now, in this case, if your T is equal to infinite, we have seen your Ts is equal to Tb. But in this case, this term is like Tb minus delta T dash. This delta T dash term came because of that alpha 2 term that is related to the R2 term, that is there is some heat loss. In that case, even at T equal to infinity, you will find that your Ts is equal to Tb minus delta T dash. So, this is your Tb, this point is your Tb, and this point is your Tb minus delta T dash. So, even at T equal to infinite, you will find that your sensor temperature is reaching Tb minus del T dash. So, it can never reach Tb if there is certain sort of heat loss. That is what we wanted to show in this discussion, just by considering the second term associated with R2, which is probably more practical situation, right, if there is some certain sort of heat loss, right. So, there are three take home messages also in this case. The first one is, dynamic condition in thermal sensors follows an exponential relation. We have seen in both the cases, right. There is an exponential relation associated with the dynamic condition. Then smaller time constant lead to a faster response. We have seen this is how the response is. So, if the time constant is smaller, it will reach to the value of Tv faster. So, a smaller time constant lead to a faster response. Then the sensor temperature can never reach object temperature if you consider that second term, that is the heat loss term. So, that is always Tb minus delta T dash. Just now we have seen mathematically as well. So, your sensor temperature can never reach object temperature in practice if there is certain sort of heat loss associated with it. Now, the question is, if your sensor temperature can never reach the object temperature, can your sensor detect the object temperature accurately? Is it possible? I want you to think. And we will probably discuss the same thing in coming discussions. Otherwise, you may think it's not very difficult. The question is, I repeat, if your sensor temperature can never reach the object temperature, how the sensor can detect the object temperature accurately? Okay. So, in the upcoming discussion, we will again consider some other aspect of thermal sensing. Before that, thank you.